Good day, ladies and gentlemen. My name is Amon Chen. Today, I would like to present our work on determination of liquid relative permittivity using a parallel wire capacitive sensing technique. This work was carried out at TGGS King Mongkon University of Technology, North Bangkok in Thailand. Here is the outline of my talk. I will start with an introduction and motivation, followed by the sensor concept and analytical model. Then I will show simulation and experimental results, error analysis, and then finally conclusion. So as an introduction, the dielectric properties of liquids are important in many areas such as chemical analysis, biomedical sensing, and industrial applications. Capacitive sensing is an attractive method because it is simple, low cost, and sensitive. However, there is a challenge when only small sample volume is available, especially for biomedical applications. So for such cases, full immersion of electrode is not possible. That's why the objective of our work is to detect the dielectric value of liquid under test and to design a parallel wire capacitive sensor that work under partial immersion. And that sensor should be low cost, simple, and accurate. We also validate through theoretical modeling, simulation, and experiment. Traditionally, a parallel plate capacitor is used for dielectric measurement, but this method is not suitable for biomedical liquid because sample volume is very small and fabrication on small scale is challenging. So to address this challenge, we propose a parallel wire capacitor that allows partial immersion while it still accurately characterizing the liquid. In analytical model, this equation is the capacitance between the two electrodes. In the case of full immersion, the electric field exists entirely in the liquid, but in our case, the electrodes are only partially immersed in the liquid, so the field is shared between the air and the material in the test. And this condition can be modeled as two capacitors connected in parallel, one for the air region and one for the liquid region. And if we use water as a material in the test, the total capacitance between the two electrodes can be written as follows. It's the summation of capacitance in the air region and the summation of capacitance in the water region. And we use analysis Q3D extractor to simulate our sensor. For the sensor, we use copper rods of length 84 millimeter, diameter of 2 millimeter, and 9 millimeter spacing between the two electrodes. Immersion of 4 millimeter depth into the liquid. And we use air, ethanol, and water as different MUTs. And this table shows the comparison between the analytical model and the Q3D extraction. Here you can see the two values show good agreement and with small differences. And for the experimental setup, we fabricated two parallel wire sensor by using copper rods, and we also use precision accelerometer operating at 1 MHz. An open short calibration was performed to eliminate the parasite effects. Then we connected electrodes to the meter and then immerse in the liquid. So here are the experimental results with three different MUTs, air, ethanol, and distilled water. And in this table, the measured capacitance values of air was 1.065 picofarad, and ethanol about 2.26, and the water was about 1.08 picofarad. And these values closely match with analytical model and Q3 extraction, so which can confirm the accuracy of the method. For error calculation, we calculate percent error to check the agreement between extracted and calculated permittivity values. This equation was used for percent error calculation. Extracted values as observed and calculated values as reference. And this table shows the three different percent error for three different MUTs. The percent error of air and water is less than 1%, while the percent error of ethanol is slightly higher at about 1.6%. This is due to the impurities, moisture, and ethanol sensitivity to temperature. But overall, the accuracy is very good. So in conclusions, we propose a parallel wire capacitive sensing technique, which is low cost, simple, and accurate. And this method is suitable for biomedical application with small sample volume, and electrodes are partially immersed in the liquid. And there is a good agreement between the results from theoretical calculation, simulation, and experiment. And so this method is reliable for practical applications such as industrial monitoring, biomedical diagnosis, and environmental sensing. So as future work, we plan to scale this concept down to the micro level for biomedical sensing, such as integrating with microfluidic platforms. So thank you very much for your attention. I will be happy to take any question.